Okay, more and more coming. So that's good. And you can see the slides, can you? All right. And then you know also that if there is this option to raise hand, so can you just click on raise hand to make sure that. Nicholas, if you just raise your hand. I'm not sure I see it, but anyway. So more and more people coming. I think you are all in all, it's around 20 students, right? So how many? Yeah, but it's sort of it sounds all reasonable. And just wait. Let's wait for a couple of minutes. Yeah, so I think now we can start, and I want to welcome you to this course on the strength of materials and the finite element method. And I'm just wondering if you can you see the slide? You see the slides? Okay, so this is quite a short course, and you know we have to have the examination in 3 weeks time, so it's quite short and intensive course, and it's going to be given online using the slides. And I'm in charge of the first part for the first 4 lectures, and my name is Sergei Sorokin. I am a professor at the Department of Materials and Production, and then it will be 2 my colleagues from also from this department. And then the course will be given both in English and in Danish, and the examination will be oral. And examination, it's up to you. You can give your answers in Danish or in English. It's entirely up to you. And then the way it will be organized is that we give you, by the end of the course, we'll give you the detailed questions. So it will be not very many questions, but each question will contain kind of the several items. And then so it will be very much detailed. And then you are supposed to explain each of these items, or bullets, if you like, orally. And then that's how the examination will be done. So it's not written examination, it's not solving the problems, it's just explaining the ideas and giving probably some illustrations for these ideas. And again, something which I have to put from the outset very clearly is that it's not like, let's say, strength of materials, full stop. It will be very much detailed. Let's say free body diagram, let's say maximum stresses, this stuff, and this stuff. So the main focus here, probably in contrast with what you had in the course on mechanics of materials, is that it's not solving problems, but it's rather explaining the concepts. And then I will begin with the kind of the reminder of the strength of materials. And then will be 3 extra topics which was related to the strength of materials from my side. And I'm just wondering if I may ask if somebody can give me the answer. This course on strength of materials, you had it in the last semester, right? Did you have the course on mechanics of materials?
Yeah, on the third semester.
And then it was Johnny Jacobsen, or it was somebody else? Was it Brian or was it Johnny?
It was Mikael. Oh, it kept. But was it Jörn or was it?
Jörn Kepler.
Yeah.
Okay. So, but anyway, this slides, I'm just asking because the slides which I'm going to show you in my part of the course, they were prepared by Johnny Jacobson, but you didn't come across him, you don't know him. Okay, never mind. So now let's discuss this first topic of the course. It's just revisiting the strength of materials. And then again, if you have any question, I think probably the easiest will be if you just either raise your hand or you can just unmute your mic and just ask the question. So what we are going to do today in this agenda for today is a kind of repetition. So I just want to remind you the basic concepts of statics and mechanics of materials. And then, so it's kind of the brief overview of the whole course you had with Joran Kepler. And then it will be followed by the exercise session. There are several exercises, but I have already uploaded all the solutions in Moodle system. So the idea will be not to do these exercises sort of from scratch, but just take a look at the solutions and make sure that you understand how these solutions are obtained. But then just to remind you the purpose of mechanics of materials and the reason why you in the architecture and design education line, you have this course. So the point is that, of course, you can design very fancy things, very nice buildings, some sort of devices or whatever, but then first and foremost thing to ensure is that this structure or this building or this piece of furniture or whatever, it withstands the loading which it's supposed to carry on. So I think it's not an option. So if you design then very nice building and then it falls apart due to the insufficient strength. So then the main point for you to study or to be acquainted with the mechanics of materials is just to make sure that the structures must be strong enough. They must preserve their integrity under the given forces. And then to do it, we have to kind of do quite a lot of stuff. We should sort of begin with the equilibrium of the whole body. Then we have to go into the stresses or into internal forces inside the body. Then we say that there are some deformations or strains, and then we sort of calculate displacements if the displacements are of interest. And then in the literature for this part of the course, this first 4 lectures, it's this book by Gary and Godno. It's Mechanics of Materials, and it may be any edition. Of course, here it's 8th edition, but it's earlier or later editions. It's still okay. And then, as I told you, the exercises which I'm going to offer you with solutions is this ones, and they more or less cover the whole sort of the bunch of the problems in mechanics of materials. So now,
Sergey,
yeah.
There's a question if we can record you.
Yes, please. Yes.
Okay, thank you.
Yes. So the first thing to mention is that then we do, and again, it's something like it's common sense. So if we consider, for example, the strength of the buildings, then we are quite certain that this building is in equilibrium, right? So it doesn't fall, it's not falling apart in the course of the building. So it's in equilibrium. Likewise, here you have this picture in the left corner of the bridge. And then, of course, this bridge is in equilibrium. Of course, if some train passes, it may be sort of engaged in some vibrations, but in principle, it's sort of basically it's equilibrium. And then in order to ensure the equilibrium, we have to formulate very simple statements that the sum of the forces and the sum of the moments acting at the structure must be equal 0. And then in general, the forces are vectors. So then they have 3 components in Cartesian coordinates, and likewise the moments are also vectors, so that in principle what we actually have, we have here in this frame here, we have three equations of the equilibrium for the forces, with I meaning x, y, and z, and three equations of equilibrium for the moments. Again, it's x, y, z. But as I understand, in the course you've been dealing with, it's quite kind of the introductory course, you've been sort of limited your analysis to what is called 2D structures. So then it was just the plain equilibrium conditions. So we have x and y directions for the forces, and we have only one equation for the moments. Then I'm not going to discuss in details these nice pictures, which just explains you the difference between what is called the active forces and reactive forces. And again, this is something which is not quite difficult to imagine. For example, if we take a look at this bridge, and then if we say that a train passing this bridge, then the weight of this train is the active force, this force which is applied to the structure now, and then it is gone. But then the reactive forces, they are sort of acting on this bridge from these pillars. So here you have this kind of the support, and then this support produces the reactive force, which is of course different depending upon what kind of active force you have. You may have heavy train, you may have light train, and then of course the reactive force will be different. But the point is that if we have reactive forces, then we have to introduce them in a very definite sense. And it's very simple. This is something which is related to what is called kinematic constraints. So for example, here in this, if you have this sliding support, can you see my cursor? Can you see it? So then here you see we have this kind of triangle, and then we have here these rollers which allow motion in the horizontal direction. And also here you can see here we have this hinge which says that the rotation is not restricted. So it means that this kind of support may produce the force only in vertical direction. Then likewise here in this picture, we also have this kind of sliding support, and then of course this force may be acting only in the normal direction. In general, we could have something which is more to the advanced. We could have forces in two directions, and we also have moments. And then the idea of sort of doing this sort of the reactive forces is that then we go for the analysis of the stresses and strains. We have to do quite a lot of idealization. So we have to go from the physical structure to the engineering model, and you see it's quite a simplification. So here what is meant is that we have this sort of a span, one span of this bridge, and this span is considered like this simply supported beam of uniform cross-section and given length, and then this bridge is exposed to the external forces and reactive forces. So then what we do, we come from the physical structure to engineering model, and then from this model, we go to what is called free body diagram. And this free body diagram, it sort of makes the step to release the supports, just to remove support. You see here you have this support, this triangle, and it sort of produces the force in vertical direction and in horizontal direction. And this is exactly what we see here. We have these two forces. And likewise here we have the sliding support, so that there is no resistance in horizontal direction, but you definitely have a force in vertical direction. So then it's here. And then this is what is called free body diagram, and this is a cornerstone in mechanics of materials. Because in order to find the internal forces, first of all, you have to find the forces acting on the whole structure, which ensure its equilibrium. So the whole concept here is that we have to make sure that the structure is in the equilibrium under action of external forces, active and reactive. So does it make sense? So we have two types of forces. We have active forces which may be different, right? And the reactive forces which are produced by the supports in order to ensure the equilibrium. Make sense? No questions? Good. So then with this reactive forces, here we have to find them. And again, this is exactly, and probably this is in this slide you see here this sort of the magic list with 12 steps. But I'm afraid you didn't have these 12 steps, right? If you, because I think this is something which came with this slides from Johnny Jacobson, but I'll try to explain, so no worries. So the point is that now we have this free body diagram, and in this free body diagram we are provided with this moment, with this force and this distributed load, but we don't know these three forces: this horizontal force, reactive force, this one, and this one. So we have three unknowns, but we have three equations, because we have sum of the forces in the horizontal direction, we have sum of the forces in vertical direction, and we have sum of the moments with respect to any point. So, free body diagram. This is the very fundamental concept of mechanics of materials, and then it is concerned with, as I say, with the finding these reactive forces. Then we have the equilibrium of the whole body, and then this equilibrium is the sum of the forces in the horizontal direction, in the vertical direction, and sum of the moments. And then I hope you remember this kind of the rules. So if you have distributed load like this, then you have to find its resultant, and this resultant acts in the middle of there it is applied, so it's here. Then if we have these three equations, then we immediately find these components of reaction forces, XA, AX, AY, and this CY. So we have found these forces, and now we do the very important step in the mechanics of materials. So now what we say is that now they ensure that this body in general is in equilibrium. But if the whole body is in equilibrium, then each and every piece of the body must also be in equilibrium, right? So this is I think it's quite obvious. So it cannot be that the whole structure in equilibrium, but some pieces of this structure are not in equilibrium. So then what we do this cut, as shown here, and we sketch again the free body diagram, but here free body diagram is not for the whole structure, because here the first free body diagram was for the whole structure in order to find the reaction forces. Now we have found reaction forces, so they are given, but now we want to find the internal forces. And then with these internal forces, I'm sure it should ring a bell for you, because I'm sure Joran Kepler explained to you very carefully these things, but it's my sort of the duty to repeat it. Here we come to the very sort of the actually simple thing, which is the sign convention. So here you see you have quite a bunch of forces and moments acting on this part of the beam and on this part of the beam. And it's not entirely obvious how the internal forces and moments are directed. And here we introduce the sign convention. So we just say that if we consider the forces and moment acting from the right part to the left part, then they must be directed as shown here. So the moment must be anti-clockwise, the horizontal force in extension, and the shear force downwards. And if we consider the forces acting and moments acting from the left side onto the right side, we say that they are acting in opposite directions. So this is M, you see here, it's in opposite direction, and then both forces also in opposite direction. It's of course due to the third Newton law of action and anti-action. And then as we again set up the equilibrium conditions, then the first thing is that it doesn't matter whether we set up the equilibrium condition for this bit or for this bit. the result will be exactly the same. The formula for the moment will be the same, formula for the force will be the same, no matter whether you consider this part or you consider this part. And the reason for this is that you have the body in the equilibrium. But the values of the forces and this moment, they may be positive and they may also be negative. And then it just says that, sends a very clear message. So if you calculate the moment in this cross section and it appears to be negative, it just means that in the real life the moment acts in the opposite direction. So if we have a force, that's horizontal force here, and you do calculation and you found out that this force becomes negative, it means that it's not in extension but in compression. So this is just the sign convention. So we don't care how the forces are actually applied. We always, and then we do this with the chopping here, we always apply forces and moments as shown here. This is sign convention. Make sense? Have you heard it from Jorn, I think? Good. So now we move on. And then we find these forces for this exactly at the point which I have shown. So we have here the slice. So then we write the equilibrium conditions. But the difference is that the equilibrium conditions here are formulated not for the whole beam, but only for this slice. And then depending upon where we chop it, here, here, or here, we have here this x dependence. But what is very important, that these equations and this diagram is valid only when we do this chopping from this point to this point. So if we do the cross section here, then it will be another expression, but then, so you have two parts of the beam. Then you solve this static equilibrium conditions, and then you find this, what is called stress resultants, because in mechanics of materials, we are talking about stresses, we are talking about normal stresses and shear stresses. And then this force NS, this is the normal, it's a resultant of the normal stresses in the horizontal direction. M, it's a resultant of stresses which are linear distributed in the cross section. And then this is resultant of shear stresses. And then you see that they are dependent upon X, upon the position of the cross section, which may be anywhere between this point and this point. So these formulae, this is something which is very important to remember, that these formulae are valid only when X is larger than A, and of course it's less than the whole length. So if we are interested in this part, then it's another story. We have to do the similar things, but it will be another set of equilibrium conditions. Then the next step is just to plot the diagram. And I'm sure you did it. And here deliberately, Johnny, he showed only this this part of the diagram. So here you see this is empty space, simply because in this sort of the kind of the reminder, we consider only this this part of the beam. So if we want to put the full diagram, then of course we have to chop here and then set up the free body diagram for this part, or alternatively for this part. But if we plot the stress resultants for this part of the beam, then it goes like this. So this is our axial force, and of course it's zero, because here we have no force here, so no horizontal force here, so of course it's zero. Then our shear force is a linear function, because here you have this x, and then our bending moment is a parabola which goes in this direction. And then we have here very important sort of the point is that we are after the strength of the structure, for example, strength of this beam. So then what we are interested in is the maximum value of the bending moment and maximum value of the shear force. And here, does it make sense? So if you have any questions, just interrupt me, and just don't hesitate to interrupt, because I know that you have done it before with Jorn, but I think it's very important just to make sure that you understand it. So in doing mechanics of materials, we are concerned with the strength. The strength is sort of defined by the weakest link. The weakest link is the point there you have maximum bending moment or you have maximum shear force. So this is where you expect failure. And then here in this diagram, we can see that we might have problem with respect to the shear force and shear stresses at point C, because here you see the force is maximum. No worries about axial force, it's all dead zero. But with the moment, you see that it looks like we have the maximum moment exactly at x equals 1. But it's not exactly, it's not true, because this red line, it crosses 0 somewhere very close, but not exactly at the point x equals 1. It's somewhere here. And then this point is the point there we should have maximum bending moment, because we have this famous relation that the shear force is the first derivative of the bending moment over the length. So this red line presents the derivative of this line. So you can immediately check it. So if you take this m and take the derivative with respect to x, you recover this formula. So it means that we have maximum moment not here, but at this point. So what we have to do, we have to find the point there, the force is 0, and then take this value of coordinate, this 21 divided by 20, plug here, and then define the maximum moment. So then what we sort of take out of this thing is that they have maximum moment and maximum force. And we have to compare this maximum moment and maximum force with what is called allowable force and allowable moments, which are, of course, controlled by the property of material. Then here, it's a very detailed summary of the relation between loads, deformations, stresses, and strains. And then we have 3 types of deformation. We have extension compression, axial deformation. We have shaft of rods with circular cross section, just like this, and we have bending. We have pure bending and we have non-uniform bending. And then these are the formula, but I don't think we have time to go into sort of all these details. It's just sort of the summary of what you did with in mechanics of materials. So we have deformation, stresses, strains in all these cases. Now we come to the next concept in the mechanics of materials, and this is the concept of the elasticity. And then the idea of elasticity, it's quite simple. So if you, for example, if you take a specimen made of rubber and you pull it, you do it in extension, and then you come from this point to point A. And then you fix your sort of here, this is how the experiment is done. So then you have this deformation and this stress. And then you ask yourself whether this is the elastic deformation or not. And the only way to give an answer is to drop the load down to 0. So if you go the same line exactly, so if you stretch and you go this line, and then you drop the force and you follow this line precisely, then you have deformation which is fully reversible. And then this is the elastic deformation. If you have, if you depart from the ideal line, then you have the inelastic deformation. And then here, this is sort of the just point. So you have the elastic deformation until certain point. And then if you continue, if you go to this point A, and then you drop down the force, then you see that you have here the residual deformation. So then it means that you have linear elastic deformation, and then here you have plastic irreversible deformation. And then if we go for the materials like steel, then this is a typical diagram. So here you have very steep growth. It's elastic deformation. Then here you have what is called yield deformation. Then you have this uniform strengthening. Then here at point D you have what is called necking. So the material, the specimen, there is the neck appears. So there is kind of the decrease, local decrease in diameter. And then you go down here until this fracture. So here the specimen falls into two pieces. So this is the diagram. Then the description of elasticity is related to this linear elastic behavior, and then this is what was called Hooke's law, which describes the relation between stress and strain of the linear elastic material, assuming that it's isotropic one. And then here it's again, it's a bit, I think it's a bit tough, but I think we have to discuss it, that in principle, if we have general 3D state of the elastic material, then we have the components of the stresses, this normal stresses, sigma x, sigma y, sigma z, and we have shear stresses. So this is how the sign convention is used. We have normal stresses and shear stresses in two directions. And then if we have isotropic material, then we have these relations to the Hooke's law. So then in the Hooke's law, we have the Young's modulus, which actually defines this the angle. So how steep is this line? Then the other thing is this Poisson ratio, which describes that if you pull in direction x, then you have kind of the decrease in the diameter or in the cross-sectional in the width in the direction y. So then it's this Poisson ratio, and then we also have what is called shear modulus, which just describes how the shear stresses are related to the shear strains. So you have distortion. So just imagine here that it's a square, but then if you have the shear strain, then it becomes somewhat tilted like this. And then the amount of the shear angle is proportional to the shear stress. And this is this general 3D case in the theory of elasticity. But then if we do the structures, like for example here, this fuselage of the airplane and this wing, then of course it's a thin wall structure. So here we have quite thin plate, and here we also have the fuselage is quite a thin shell. And then what happens is that if it's thin enough, then we ignore the stresses in the cross-sectional direction, and then we have what is called plane stress field. And then this plane stress field is the simplification of these things, assuming that we have here, we have sigma z is negligible, and sigma tau zx and tau zy are negligible. So this is 0, and these two guys are also 0. And then this is what is called plane stress. And then if you cross out these components from, from this system of equations for Hooke's law, then you end up with these equations, which still, of course, they inherited this Young's modulus, Poisson ratio, and the shear modulus, but they are a little bit simpler. So then it just means that there are no stresses in the z direction. So now just imagine that here you just chop the piece from this wing, and then it's quite thin. So then nothing across the thickness, but in plane you have these stresses in x direction, y direction, and shear stresses. Then the next thing in the theory of elasticity, this is the concept of the stress transformation. And this concept, it's quite sort of the involved, but then the point here, the underlying idea why we bother about this inclined cross sections is that, again, we are interested in the strength of the structure. So our ultimate goal is to make sure that the structure, no matter what the structure is, it's an airplane, fuselage, or the building, or whatever, it's strong, it withstands the given forces. And in order to make sure that it's able to withstand the given forces, we have to find the maximum stresses. Because what we do, the way we do the design of the structure, is that you have the real structure, you model it with means, let's say here in mechanics of materials, as a rod or as a plate, in finite element method, and this is something which you'll just discuss in this course a bit later. You do this, what is called finite element discretization, but your ultimate goal is to find the maximum stress. So you have the, and let's say, in other words, you can say we are interested in finding the weakest link. So the point where we have maximum stress. And then we calculate this maximum stress for brittle materials. We find what is called equivalent stress, but we'll discuss it a little bit better later for the materials with plasticity. And then we compare this maximum stress or equivalent stress with the allowable stress. So this is our main goal. We have to determine the maximum stress and make sure that this maximum stress or equivalent stress is not larger than what is permitted for given structure. So this is the ultimate goal of mechanics of materials, to ensure their strength. And then in order to do it, then we have to dig into these sort of the things with the inclined cross sections, because the whole point is that if you have found the, for example here, if you have found the stresses in the cross section like this, which is perpendicular to the axis, then you of course you have the simple formula that stress is force divided with the area. But in some cases, and I explain it in a second, in some cases we are interested in the inclined sections, something like this. And then if we introduce this rotation, so here this is the cross section perpendicular to the axis, and here it's sort of it's tilted somehow, and then the stress is not this one anymore. So this is something which is quite important, that the stress here will be different. There will be a normal stress, but also there will be shear stress. And then for some materials, it really makes difference. Some materials, they are quite good in resisting the tensile normal stress, but they may be quite vulnerable in resisting the shear stresses. For example, if we take something like composite materials where you have matrix and you have fibers, then the fibers may be very strong in resisting extension. But if you introduce kind of the shear, then this material becomes much more vulnerable. So that we have to be able to calculate the stresses at different orientation of the cross section. So the story is that we have two things in mechanics of materials. We have stresses acting at the point, but unfortunately we cannot say that this is the whole story, because in the point we have what is called stress or strain tensor. In order to find stresses as force resultants, we have to specify the cross-section, and depending upon the orientation of cross-section, like this and like this, the answer is different. So then in order to sort of accomplish this task, to identify the critical state of the structure, we have to do this stress transformation. And I think you had it with Joran, right? Have you seen it? These pictures. Yeah. So then it's quite tedious derivation, mathematical, and I definitely don't want to go into this to the technical details. You have done it with Joran. I just want to convey the point here. So what is the reason? So why do we bother to do this stress transformation? And we bother to do stress transformation because we want to ensure that the structure withstands given loading. And there are different types of the failure. And then it might be the case that if we have found the stresses in this system of coordinates x and y, it might be the case that this sigma x, sigma y, and tau xy, they are not the largest. That the largest stresses, they exist somewhere else. And we have to find these largest stresses. And in order to do it, we have to do this transformation. So our ultimate goal is to do the following thing. We have the structure. It's a very complicated 3D object. We have to find the point in which we have the maximum stresses, and also we have to find the value of this maximum stress or equivalent stress. And then this is exactly where we find the point, and then we do this rotation, and then actually this is what is done in finite element method. So then you'll discuss finite element method. This is something which is already built into the this software of the stress information. So here I think this is something which is more confusing than sort of explaining. So this is just shows you that depending upon how you do this rotation. So now what happens is that you have this system of coordinates x, y, and in this system of coordinates you have the given values of the stresses, and then you totally start to rotate, and it goes like this. But then I think we can survive without it. What is really important here is the concept of the principal stresses, because the principal stresses are what we are actually after. We want to find the maximum normal stress and maximum shear stress acting at the given point of the structure, because this is exactly where we do the assessment of the strength of the structure. And then there are, depending upon whether this material, what are the properties of the material, we may have a problem of the failure due to the maximum shear stress, and we can also have the failure for example, for the brittle material due to the principal normal stress. So then we also have to we plot these diagrams, and then these principal stresses, they are found in this formula. So here this is the end result. So we have this sigma 1, 2, these are two principal stresses, and they may be in compression, they may also be in tension. So then we calculate this sigma 1, sigma 2, and then we also calculate this maximum shear stress doing this formula. And then if we are working with something like cast iron, then the killer for cast iron is the normal stress in the tension. So then we just take largest of this sigma 1, sigma 2, and we compare this with what can be withstood by this specimen made of cast iron. And then if it's something like conventional steel, then for the steel, it's more sort of vulnerable for the shear stresses. And when we calculate this maximum shear stress, and we compare this maximum shear stress with what is allowable. So the concept of principal stresses is introduced only for the sake of the strength of the structure. In order to check the strength of the structure, we have to calculate principal stresses at any point of the structure, then compare these principal stresses with allowable stress, depending upon what is the material we are working with, whether it's a brittle material or whether it's a material with plasticity. Make sense? Do you remember these things? You're a bit disappointed. But again, of course, what I'm sort of talking about now, it's sort of the helicopter viewpoint. It's very fast sort of browsing mechanics of materials. So we, in order to make this sort of identification of maximum normal stresses and shear stresses a bit faster, we do what is called Mohr circle. And in principle, down to basics, this Mohr circle is just a visualization of all this stuff. So we have all this stuff, all the stress transformation, principal stresses. But in principle, all you have to take home out of this is this Mohr circle, because it immediately gives you the answer. So you have the, and it's there a lot of details here, so we can safely skip most of them. So what we really sort of have to take here is that, so this is at this point gives us the maximum tensile stress in the given point of the in the structure. Then this is the minimum tensile stress. Here it is presented as if here you have extension here and here, but in principle this point, it may also be located here. So then it will be the maximum compression stress, this one. And then this point is the maximum shear stress. So in principle, all what matters is this point, and this point. And the way to plot this circle is exactly what we have seen in the previous slides, here and here. So this is just the technicalities which sort of condensed into this circle. And what you have to remember is that if we have the brittle material, then our main concern is this value of stress. So we take this value of stress and compare with the allowable for the cast iron. So if we are within the allowable stresses, then okay, nothing will happen, will be no failure. If we have the structure made of the steel or the material with the large plastic deformations, then we have to take this value. It's maximum shear stress. And again, we compare this maximum shear stress with the allowable stress. And in some cases, we may also be concerned with this point. There we have the minimum stress, but it's relevant if it is negative, because just let me show you one step back. In principle, this stress sigma 2, here you see you have minus. So in principle, it may be negative, because of here you have this sum, here you have minus, but here you have the shear stress. And if it's very large, then it's entirely possible that sigma 1, of course, you have this plus square root, so it's positive. But if you take second, you have this minus this, and it may be negative. And in the Mohr circle, or maybe it can be shown also here, it's sort of simply moved into this area, so that you may be interested not in the sigma 1, but in sigma 2, if it's negative. So then this Mohr circle, it sort of gives us the way to immediately assess the strength of the structure at the given point. And then again, this is something which we have to remember, that we have the three-dimensional structure. So that this kind of Mohr circle has to be plotted for each and every point in the structure. And then this is something which we can do in using the simple models of mechanics of materials. But if we do this advanced mechanics of materials and finite element model, then this is what we do with finite elements. So then when you'll continue looking, studying the mechanics, the finite element method, then just keep in mind that the end result in the finite element analysis is basically the same thing. So you found these principal stresses and maximum shear stress at each and every point of the structure, at each and every point of the bridge, each and every point of the piece of furniture, each and every point of the building. And then you take the largest values and compare with allowable stresses. And if you have only one point, there you have this violation of the strength condition of the strength, then you must redesign the structure. So the chain is not stronger than the weakest link. So if you have the single point in very complicated structure, there your normal stress exceeds allowable stress, or your shear stress exceeds allowable shear stress, then you have to redesign. Make sense? No questions? Yeah, so this is just example. And then we have to discuss this sort of the failure criteria. And then the question is, do you kind of the fancy to have a short break, or you sort of still feel that you can carry on with no break? 10 minutes break maybe? Okay, so now it's sort of the 7 minutes past 9. So then let's say 9:17, okay, or 9:20, let's say. Okay, good. Continue. Are there any questions about the previous part? It was very fast, I understand, but yeah. No questions? Just don't hesitate to unmute your mic and just ask. No? Okay. So let's continue, and now we come to this point of, yeah?
I have one question.
Yes, please. Yes, please.
Regarding you had, I don't know what slide it was, but can you go back a few slides?
Yes.
Oh, not that far. It was regarding the principal stresses. Yeah, the top right corner, there's this formula. When do you use that?
So this formula tells you how to find the stresses for arbitrary angle theta. So you see here you have the angle. So just let me show. So this is the picture. So you have found the stresses in x and y directions. And then, but it doesn't mean that they are the largest. So what you want to do, you want to find the stresses if you start to rotate this square and you tilt it to amount of theta. You do this rotation. If you tilt it like this, then all the stresses become different. And the way they're changing, it's defined by this formula. All by this. In principle, it's the same thing, right? This formula and this one. So it just tells you how the stresses x sigma x, sigma y, and tau x y, how they change if you rotate this thing. And the purpose to do this stuff is to find the maximum normal stresses and the maximum shear stress. So in a way, this is a formula. There you have cos and sine, and then if you just exclude cos and sine, you have this Mohr circle. So it's all the same story. This formula and this picture. So this picture is just the graphical presentation of this formula. And the purpose is to find this stress, and this stress. Does it answer your question?
Yes. Thank you.
More questions, please. No questions. Okay. Okay, but again, please, sort of of course, I understand that this part, this introduction, the introductory part of the course is just to remind you what you did before. So this is something which is was quite fast, but just to recap the key concepts. And now we come to a bit closer to what we are going to do in my part of the lectures. In the remaining 3 lectures, it's kind of a little bit advanced look into the details, specifically in the details of failure. So then we have a failure here. This is the sort of nice pictures, not very nice, but anyway, you see here this broken glass, and here you have this wooden beam broken. So then this is something which we don't allow in the real life. So I think it makes perfect sense. So then whatever we design, we don't want to have this, and we don't want to have this. So we have to ensure that the structures are strong enough to withstand the external loading. And then the very first thing, which I probably already mentioned, but it's something which I have to repeat again, that then we do mechanics of materials or advanced mechanics of materials for finite element method or whatever. We always have the situation that we know the forces. The forces are given. We know the material. Material is also given. And then we have to design the structure to withstand given forces, which is made of given material without a failure. So this is the idea of reliable design. So you know the forces and you know the material. Doesn't make any sense to design for the unknown forces. Doesn't make any sense to design with the unknown material, right? Because it will be completely different depending upon what kind of material you use. So, and for you as sort of students in architecture and design, I think it might be so that maybe you don't think about it that much, but I hope it makes sense, right? So then you do the design of the structure. You must be provided with the forces, and you must be provided with the material properties. Now, we have this, what is called static failure. And then the idea, again, this is something which I have sort of explained to you, that any chain is not stronger than its weakest link. So here it's something which sort of clearly shows this sends this very simple message. So you have very complicated structure. You may have something like, I don't know, you have the airplane. And then in order to design the new type of airplane made of new material, you have to be able to identify the weakest point, the point where you have highest stresses, because precisely at this point, you expect material failure. And here you have this kind of interaction between the structure and the material, because the shape of the structure gives you a distribution of the forces, but the failure is dependent upon what is the material you are using. And the simple and more obvious to the division is this ductile or brittle materials. And the difference between these guys is very simple. So the brittle materials, they are not able to withstand plastic. They don't have any plastic deformation, no plasticity. It just sort of it has very small deformation in elastic region, and then it breaks down. So there is no possibility to accumulate the energy in the plastic deformation. So that's why brittle materials as cast iron and glass, they are not that much used in structures. So we definitely prefer to have the materials which are ductile, materials which are capable to accumulate energy in plastic deformation. So then the failure process depends on the nature of material. But unfortunately, and this is something which we also have to be aware of, and this is extra complication in the design of the structures, is that if you have the ductile material, it's not, unfortunately, 100% secure that it will fail with the large plastic deformations. It's possible that it will fail, the failure will be in brittle form, depending upon what are the principal stresses. So this is something which, of course, we are not going to discuss in details in this course for you, but this is something that I think you have to be aware of this. And probably we'll somewhat we discuss it a bit later, then we start talking about the fatigue phenomenon. But the point is that if you have a nice steel as a material for your structure, and then you are sort of aware that in all likeness it will sort of deform with significant plastic deformations. It's not necessarily the case. It may have a failure as a brittle material, and this is an extra complication. And then another thing is that we can also have this stability failure or buckling. And this buckling will be, I think you discussed a little bit buckling with Joran Kepler, right? You remember this Euler force and stuff like that. So then it will be, the buckling is a disaster. So this is something which is sort of absolutely impossible for the real structures. And that's why there will be special lecture on buckling in this course. I think this lecture will be given by Brian. But then the idea of buckling is that you have, and again, so probably it's a good idea just to remind you the concept of buckling. So what we do then, we discuss buckling. Some people say that we analyze the stability of the structure. And it's a little bit incorrect, because what we do in reality, we don't analyze the stability of the structure. We analyze stability of the given equilibrium shape of the structure. And here, I think in this right down bottom, it's exactly the point which I want you to be aware of. So what happens is that we have the ideally straight beam. And this ideally straight beam is exposed to this compression force. And of course, this force is balanced by the force in the bottom, so that we have this beam in equilibrium. And what we do with this Euler analysis, we analyze the stability of the straight shape of the beam. We just say that we have equilibrium, but it may be straight and it may be curved. So then we do the stability analysis. We analyze stability of the equilibrium position. And the end result with the Euler analysis is that if the force is small, then this straight configuration is stable. So for small force, the straight equilibrium configuration is stable. So if you disturb it, then it will return to the straight configuration. But as soon as your force becomes larger than Euler force, the straight equilibrium configuration becomes unstable, but the curved equilibrium configuration becomes stable. So this is very, very simple, but it's very important that the missing word very often is equilibrium. So we have here stable straight equilibrium configuration, and here we have stable curved equilibrium configuration. And then the critical force, this Euler force, is the division line. So then this is still stable, and then this becomes unstable, but this becomes stable. Okay? Make sense? Good. So now we go to the next slide, and here we come to the, it's very fancy subject. It's very interesting, and there are a lot of the gray areas in this thing. It's material failure. So what we actually mean by the failure, and for the what you did in the mechanics of materials in this first course, it's of course this division between these ductile materials and brittle materials, and then it's these pictures, they tell the whole story. So if you have this necking, you see this neck, then this is the material which has very, very profound plastic deformation. You can see that the length of this element, probably it was before the force was applied, and then it's not yet there is not yet fracture. So here it's still integrity is maintained, but you see how much longer it has become, right? So you see this elongation, and this elongation occurred at the expense of this necking. So you see you have this necking, and then of course here it becomes more compliant, and then you have this large elongation, and then probably quite soon, if you keep on pulling this this bolt, then it will be a fracture here. But this property of the ductile materials, this is something which is very, very helpful, because it just tells that if we, in our analysis, if we were a little bit off in the assessment of the forces or in the assessment of the actual strength of material, we are not yet in dire straits, because this plastic deformation, it may kind of smear out all these uncertainties. And this is actually what we are going to discuss tomorrow in my lecture on the stress concentration, because for the stress concentration, this the property to have this plastic deformation is a saver. So this is something which helps us to carry on with the design of the structures. Whereas with the brittle materials, it's as it's said here, so you have instant crack formation and propagation, and then the structure just falls straight away. So it doesn't send the message that it's in a real danger of fracture. So in simple words, here, if you take a look at this thing, then you can easily understand, this bolt is very likely to break very soon. He is quite likely to be broken. But here you don't see anything before it actually falls into two pieces. Make sense? Now, how we can distinguish this ductile and brittle materials? And of course, this is kind of a rule of thumb, but the true story, and again, this is what we'll discuss tomorrow, I think, is that you cannot be 100% certain that the material which is ductile keeps on being ductile, And also you cannot be sure that material which is sort of the brittle, it's always brittle. So this kind of the transitions, it's all very much dependent. The simplest example of the factor which controls this sort of the transition is the temperature. So if you if you have the something like cast iron, and then you raise the temperature so that it's almost melted, then if you have this high temperature, then of course it becomes plastic, because by the end of the day, if it's melted completely, then it's just like a fluid, right? The metal above the temperature of melting. And then if you start to decrease the temperature, then it's opposite. So then you have solidification for cast iron, it becomes brittle. And if you take the steel, and if you start to pull temperature down, down, and down, if you say, let's say something like minus 100 degrees Celsius, then this nice property of plastic deformation is gone. And then the very nice ductile material as this steel, it becomes as a cast iron at the temperature of minus 100 degrees Celsius, let's say. And if you raise the temperature to say minus 20 degrees Celsius, then it recovers its properties. So the point is that all this sort of the division between these two types of materials, it's dependent upon temperature. It also depends upon the speed of loading. So if you have slow load, then you have it's more likely to have this ductile plastic deformation. If you apply fast loading, then it's more like a brittle material, and so on and so forth. So it's something which is very, very different. And it becomes even more complicated if we go to the modern materials, to the materials made of composite materials, where you have matrix, you have fibers. Then it becomes a complete nightmare. Whether you can say whether brittle or ductile, plastic deformations, elastic deformation, it's very, very complicated. But this lies beyond our course. And then, of course, the criteria, failure criteria, so we'll discuss it in a minute. Then it's just sort of the way to kind of understand what we allow for the structure to withstand and what we don't allow. And then the very simple sort of the quantity is a safety factor. And then it just says, so how far from the failure we may go. So if we have the structure which is made of very simple material, isotropic material, and then we know for sure the conditions, what is the temperature, what is the load, and stuff like that, then the safety factor may be quite small. It may be something like maybe 5% exceeding 1.05, something like this. But if we are in the gray area of not yet fully determined the exploitational conditions, then safety factor may be really large. And then, of course, this design guidelines is what we do in order to ensure avoid the failure, because failure is not an option, of course, in the design. And then with the ductile materials, and first of all, I have noticed here, please just probably you can do it with this modern means. Of course, this is a typo in this. If you take this, look at the formula in the left bottom, then of course there must be 3 tau xy squared. And you see it makes perfect sense, because it must be coherent with respect to displace dimensions, right? So here you have sigma squared, product of sigmas, and then of course there must be tau squared. So please immediately put some notes on this in the slide 21. Bottom formula sigma von Mises is this one. So then, and I just want to have you discuss with Joran this failure criteria, von Mises and Tresca. Do you remember this? Failure criteria. Yes. Okay. So now let's sort of just recap these things, and now I go a little bit more into details, because this is something which what we have to take with us in this advanced course. So before, in the first part of the lecture, it was just sort of the hovering on what we have known, but we are not going to use that much. But here, with the failure criteria, this is something which we'll be going to use in this part of the course. So then, what is the failure criteria? So this is actually quite interesting and important thing. We have the possibility to do experimental work in the very limited sort of framework. There are many cases, for example, 3D uniform extension, which are virtually impossible to do experimentally. So we are sort of limited to the very simple experimental facilities, and then the sort of the normal way to do the experiment is just to take the specimen, put it to the machine for the extension. It's very easy. It's available virtually everywhere. Then another way to do the experiment is to take the specimen and put it to the machine for torsion. It's also very simple. And then, of course, we have this 3D three-point bending. But what I want to add as one more option is that we can do the combined action of the torsion and extension. So these are the ways to do the experiment. And then if we do the experiment, then we can really see this necking, and we can stop at any time and drop the force back to 0. And then we can easily see whether we have the plastic deformation, irreversible deformation, or if we have elastic deformation, fully reversible. So then we do this kind of things: extension, torsion, extension plus torsion, 3D bending, 3-point bending. Then we can stop at any time and assess the specimen. For more complicated cases, it's very difficult. So then what we introduce here, we just say, so we do this experiment. Let's say we do experiment with the uniaxial tension. And with this uniaxial tension, we immediately identify the yield stress. We find the stress which is in a uniaxial tension, which produces the plastic deformation. Now we say, so we have to define what is the true reason of transition from elastic deformation to plastic deformation. And then this sort of the reason, it is mathematically present as a criterion. So we have to find some number which uniquely tells us whether we have plastic deformation or elastic deformation. And this is what is called criterion. And for ductile materials, there are two criteria. One is called von Mises criterion, and another one which is called Tresca criterion. And immediately in this picture, you can see that you have this ellipse, right? And then you have this dashed line with this sort of the, which lies inside this ellipse. So then this ellipse, it's what formulates von Mises criterion, and these straight lines, they define what is called Tresca criterion. And the point here is that if we have the stress state such that the principal stresses are inside this area, Then we have elastic deformation. If we go to the boundary, and here we have some differences between Tresca and von Mises, we have sort of the transition to the plastic deformation, and then if we jump out, we have plastic deformation, irreversible plastic deformation. So this is how it is. Then the underlying concept of this criteria is that no matter what is the real state of material in the given point, we just have to calculate this sigma von Mises, no matter what are sigma 1, sigma 2, and sigma 3, and compare it with what we have in the case of uniaxial tension. So if the von Mises stress in the given point of the structure on the given loads is less than what we have experimentally found for the specimen in extension, then we say that the structure of in this point we don't have the plastic deformation. If our calculated von Mises stress is larger than we have found experimentally, then we say that it's going to be irreversible plastic deformation. So it means that it's no-go. So here we have a very sort of important. There are very important two steps. The first step is that we do the testing of material in uniaxial extension, and then we find this yield stress, and then we calculate the von Mises stress for arbitrary state of the material, and then we compare von Mises stress for the so in principle, this von Mises stress, it's a kind of the equivalent stress. So this is the stress which would exist in the, if we convert the loading to the uniaxial extension compression. So it's the idea of von Mises. And then if we do the Tresca criterion, then it's the same thing, but the formula is different. Of course, the Tresca is just sigma 1 minus sigma 3 a half. And then, interestingly, that here in this, and this is quotation from this book by Norton, there are these experimental points. And then you see that there is no that much difference between the Tresca and von Mises criterion. So in principle, they both are good, but also you can see here, it's very important that there are no experimental points here. So we have experimental points in this right half plane, you see here and here. And this is again, this is what I explained to you, that it's very difficult experimentally to have this the biaxial compression or this combination of the stresses, so that the experiments cannot cover the whole sort of area. But we say that if this hypothesis work in this area, then probably they will work here. And so far, our experience in doing the strength analysis based on this von Mises criterion, it's very satisfactory. So although we cannot confirm experimentally that this is transition zone for this combination of stresses, in principle, we know that no failure occurs with this structures. Yes. And then what else can be said here? Just let me think. So this is of course very important, but this kind of things what we have discussed in the last part of the lecture, this is something which I will refer to then we talk about the stress concentration and fatigue. So these things just try to be more attentive, because in the first part it was kind of just to the helicopter viewpoint of the theory of strength of materials, but here these 3 slides, this is something which we'll refer to in lectures tomorrow and after tomorrow. So if there are any questions about these things, I think it will be a good idea to ask. Yeah, okay. So, but in principle, it's it's not the end of the day. So I'll be online in this Teams until 11:45. So then, if you have any questions about these three things, and likewise, if you have any questions of the previous part of the lecture, you are most welcome to ask me, maybe just making a call or writing a mail. And then as for the exercises, then I think if you just go to the Moodle, then you'll see the exercises and solutions. So in principle, what I present here is both the exercises and the solutions, because it's not what you are going to have in the examination. As I told, the examination will be on the concepts, what we have discussed during the lecture. Here, this is just to recap what you have done in mechanics of materials, and then what I suggest again. So please just take a look at these problems and solutions, and then if you are quite happy, then if you say, okay, yes, of course, it's all very simple, I understand it, I understand that, then that's it. But if you have any questions about the way the solutions are obtained, about some drawings, some sort of the formulae, then I think it will be the best if you just approach me, and I will be very happy to give you clarifications how it is actually done in these solutions. So my point here is that you are not supposed to put these solutions aside and try to do it all by yourselves. Instead, you just take at the problem, look at the problem formulation, at the solution. So if you understand the solution, take the next one, do the same. If something you don't understand, ask me. Okay? Okay, so then I think it's more or less all by now, and I say I'll be online until 11:45. So whenever you want to ask questions, just make me a call, and I'll answer. And if you have any questions straight away, just ask. No? Not straight away? Okay, so then I'm available.